In this video, we will discuss about 1 in 60 rule. Let's put that down. 1 in 60 rule. What is that? We'll begin with a right angle triangle. So here's a right angle, and here's an acute angle A. Let's name this X, Y, and H. From secondary school math, we were taught that sine A equals y over h, cosine A equals x over h, and tangent A equals y over x. So what's special about these? Nothing. Until we look at the table here, I've put down some numbers, some integers, representing the angle in degrees from 0 to some numbers greater than 30. And also, column B, column C, you see 60 sine A, 60 tangent A. If we find an interesting fact, for up to 14 degrees, let's say that's tangent 14 degrees multiplied by 60 is 14 point something. So the integral part is exactly the same as the value of the angle in degrees. For sine, this value goes up even higher to 30. So up to 30 degrees, the integral part, after getting the sine and multiplied by 60, we get exactly the same value, 30, if you ignore the decimal part. So with that knowledge, we come back to this triangle. And let's have an example here. 60 and 14 degrees. As we have checked, up to 14 degrees. And what is y? We know that tangent 14 degrees equals y over 60 for this triangle. So y equals 60 tangent 14 degrees, which is approximately 14. So y is approximately 14. Now, what if it is only 30 here and it's 40 degrees? What do? I can extend this line, add another 30 here. So the whole thing here is 60. And we know that here is approximately 14. And because these two triangles share the same angle, 14 degrees, they're similar triangles, they have linear scale. So we take out our flight computer. We put 14 above 60, or we put 60 below 14. And then we look at 30. What is that? 7. So the length here is 7. So any angle A, you put A above your 60. And then the length x, find x, and with the value here. That's how you use the flight computer to find the length of this question mark for A between 0 and 15 degrees. Okay, not including 15, but less than 15 degrees. Another interesting fact, as I put sine in the table as well. What do we do with sine? So let's say we have another triangle here, and then name this A, B, alpha, and beta. Mathematicians have proved that opposite angle has a special relationship called the laws of sine. So opposite sine, opposite angle. B over sine alpha equals A over sine beta. It's already proven. Just memorize that. What's special about that? If you put in some concrete numbers, let's say 6 degrees, 3 degrees. Remember, for angles up to 30 degrees only. And if this side is 10, what is the length of this side? So let's call it B. B over sine 6 degrees equals 10 over sine 3 degrees. And we can divide both sides by 60, right? We divide both sides by 60. Then B over 6 approximately equals to 10 over 3. Because for this interesting fact here, up to 30 degrees, we can do that for sine. Now, we can then divide both sides by 10 because our flight computers shows 60 instead of 6. Okay, so flight computer. We know 3 degrees and 10. We usually put distance in the outside scale. So outside scale 10, inside scale 30. And then we find black 60 and read that number. That's the answer. What is that? 20. Great. So B is approximately 20. That's it. So this only applies to planar coordinate system. Everything, sine, cosine, everything here only applies to planar coordinate system. For some extra bonus, let's talk about spherical coordinates. You can skip this part. So if we have a sphere, and then this is the North Pole here, and then this is the equator. So this is right angle, and let's say this angle, or what is this angle? For instance, 0 degrees east to 90 degrees east. Then this is right angle. Interesting. On a plane, the internal angle, the sum of internal angles is always 180 degrees on a plane. But on a sphere, or on a spherical or curved surface, anything non-plane, then the story is different. So for this triangle on a spherical surface, we get 3 right angle. That makes the internal angles, the sum of internal angles, 270 degrees, which is very different from what we learned in secondary school, because we were only taught about the plane coordinate system. So how does it affect flight planning? When we do a flight plan, we only just take a very small area, which is approximately okay. It's very similar to a plane. And our map is actually projected onto a plane. But as we go near the pole or larger area, we need to take the projection into account. So some conic projection, some cylindrical projection, different kinds of projection or plane projection. So the angles not uniform, not linear. If we have a very long distance, we don't want to measure the angle. Try to take the center point, put your protractor near the center to take an average. Okay, so that's all for this video.